All right, I'm Greg Tucker. I had a talk yesterday about storage acceleration with ISA-L. So this talk is too short, but unfortunately he had a personal emergency. He couldn't make it, so I'm filling in. I'll try to do the best I can, but he's really the expert on Ceph. But he sits right next to me, so I've absorbed a little bit from him. I'll see how well I can do. And but this work was a combination of a number of people at Intel that work on Ceph. So agenda is a little bit about Ceph and some of the efficiency and security features that are in Ceph, and in particular about how this hardware acceleration POC was done. And then a little more about Ceph data services, including their Ceph Erasure Codes and how it's currently done. And you can use ISA-L for erasure coding acceleration and compression hardware acceleration using QAT, which is our Intel QuickAssist technology, the specific hardware offload engines from Intel. So first about Ceph. Ceph is open source. Probably everybody knows it. It's a distributed file system, very popular. It's hardware agnostic. It can do lots of different interfaces, block, file, and it's highly durable, available, has lots of modern features, replication, erasure coding, and it replicates and rebalances dynamically. And that's why it's very popular. Ceph uses just crush map for data placement and like I said, lots of other enterprise features. And that's why it's the top backend storage, or not backend, storage for people using OpenStack. So there's a poll of people using OpenStack, and most are using Ceph. It's the most popular. So Ceph has a distributed over your nodes, and then disks are the client talks to an OSD, as they call, and OSDs talk to disks through a variety of backends. So you can, the OSD does the distributed part really, and the backends are your local storage that are local to the disk. And this can be directly through a local file system, and they can, or more directly, which is called BlueStore, I believe, where there's also a key value backend to Ceph. And so if you do the POSIX interface, there's a number of different local file systems. You can use BTRFS, XFS, EXT. And then, where you do the erasure coding and compression, you can do at various stages. Of course, compression you could do anywhere probably, but where it's built into Ceph is in this backend store. And then you can do in multiple places there. You could do it in the file store, of course, or you can do it natively in BlueStore. And encryption, you could either do it, again, at the file system level or some self-encrypting drive. But erasure coding is done in the OSDs. I think this is just the same for it. Encryption, it can be done in different places too. At the RBD block and natively or in the RBD object. Tushar probably had points for each of these, but so as far as offload goes, of course, there's these trade-offs. If there's a latency inherently when you go hardware offload. And the most if you had a PCI attached card, more if it's off of QPI, which is basically it's in the chipset. Less if it's an on-chip acceleration, and the lowest latency is when you're doing it on core. But and there's a trade-off also in flexibility when you're doing it on the CPU. It's usually easiest. You can usually use a synchronous interface. But whether you're using an offload that's reconfigurable, maybe not so bad, but a fixed function, certainly less. So ISA-L is like I said before, is an all software library that does the acceleration. QAT is our hardware acceleration. So just a little review of ISA-L. If you remember from my talk yesterday, it's all complete software library. It's open source. It's ported to lots of different operating systems: BSD, Linux, Windows, and it's it's a collection of low-level libraries that are all software and lots of hand-coded assembly. And Ceph is one place where it's been integrated directly, HDFS and Swift also, and lots of other places I mentioned yesterday. But QAT is quite different, of course. It's hardware offload. And QAT, QuickAssist technology, has multiple features, actually, multiple functions that it's offload for. It'll do crypto operations, bulk crypto, and also other secure key management and key generation, and other offload for public key encryption and compression. And there's different places you can integrate it. There's a PCI card you can plug into your to offload. It's also available on chipset, and on some chipsets that enable it, and some SoCs will actually build right into it. And there's also various ways you can access the hardware offload. There's libraries, there's a kernel interface, and there's also patches to other OSs and standard libraries that you can access and more directly. Or there's a way for applications to access it, an API for applications to access it directly. More specifically, there's a way you can use OpenSSL, and it'll offload directly to hardware. And built into I think it's in series now, a kernel interface or a crypto interface or patch for the Linux crypto framework. Or for compression, there's a patch to zlib where you can just call it zlib as you would, and it'll offload to hardware. There's I think it's BTRFS that's being integrated. Ceph, it's also in Hadoop and a number of databases. There's a way that you can have the database compression go through the hardware acceleration. So erasure coding has been integrated into Ceph since Hammer, which I think is 2 releases ago of Ceph. And so the hot offload for compression, ISA-L has been integrated already, and I think that's in Blue Store is where that lives. And there's various places for the QAT offload. So what we were talking about here is we're going to use it as integrated into BTRFS. So the QAT offload for compression integrated into BTRFS, and then Ceph using BTRFS. But for compression, it's also possible to use blue store for and QAT offload. But I believe that that's a work in progress. And encryption, there's a Rados, so that's one of an implementation of ISA-L and QAT, but work in progress. So with Ceph and Erasure Codes, using our software offload, like I said yesterday, ISA-L has already been integrated in lots of different places. And so now that we can do it fast, it's not so prohibitive as it was before for running on your standard servers. But in Ceph, anyway, how it works is the Ceph client on a write talks to one OSD, and then that OSD, the Erasure Codes are done, the math for them is done right there, and then it talks to the other OSDs to write the fragments. And so normally it's very CPU, that part was very CPU intensive. And then on read, reconstruct, the same kind of goes backwards. The client talks to one OSD, and then it talks to the pool. So what I understand, it was fairly difficult to stress the system enough so that you could see the throughput difference for just Erasure Codes. And I'll talk about the setup later, but Tushar and his company did this and found that they could limit the throughput with Erasure Codes, and they found that using ISA-L had some measurable benefit to throughput. Probably you see a lot more in CPU utilization, but it can also limit the throughput. Now, QAT, Ceph and QAT, they did compression. So in this setup, the compression is very CPU intensive, of course, more than Erasure Codes or most other algorithms. So they turned on compression, and you can see the trade-off between picking a compression ratio or an algorithm, compression ratio, and the CPU utilization. And so in this case, they did LZO and GZIP and BZIP2, and and the line is the CPU utilization. And so when you use the higher compression levels, you're spending all your time doing compression, really. So then they added QAT offload for compression, and as you can see, this is with two levels of QAT offload: what they call level 1 and level zip, or level 6, and QAT has offload for deflate. So when they added QAT, you can see that the CPU utilization goes way down, and they can keep the compression ratios up to levels of standard zlib 1 and 6. So a bit about BTRFS. I understand BTRFS is a common back-end store to Ceph, and that's because it's got lots of modern features like copy on write, which make it uniquely suited for Ceph clusters. But when you do it in the kernel, you're using extents in the virtual file system are 128K, so you're compressing 128K at a time. And by sticking to deflate, because it's standard, you can do compression with hardware and decompression with software, or decompress something that was compressed in hardware. So, and this is a representation about where the hardware lives when it's in your local file system, of course. This is done in the kernel. And after the virtual file system layer in the Linux kernel crypto API, it's calling the QAT offload, going off to the hardware and then coming back, and then goes to the page cache, goes to the media. I guess there's another way to say that. QAT internally is, writing in 4K pages, but the whole extent's 128K. So this is a bit about their setup. What they did is it took a storage Ceph cluster. They took a JBOD with 12 SSDs and 2 NVMe drives. So, and then they were stressing this with another system and a 40 gig NIC link. And then FIO was used to generate traffic. So, and then another thing they found that it was actually difficult to, even under this circumstance, to stress the SSDs. So normally I understand you use one OSD to talk to each disk, but in this case they put 2 OSDs talking to a single SSD, so they can get the throughput. And then they put the 2 NVMEs were doing the Ceph journals. Some system details, but what they can see is, again, when you do hardware acceleration, the CPU utilization goes way down. And then the time plot at the end, one was with, when you're using zlib, of course, it takes much longer. And it's when you're using zlib level 3, you've pegged the processor, basically, and you've doubled the time to write it out. You can do better with other compression methods, but the CPU utilization is still pretty high. But with adding the QAT offload, you could do both. You do it in half the time, and you keep your CPU utilization low. And, for reads, the benefit wasn't quite as obvious as the writes. So anyway, here's more information. You can look up details about QuickAssist and or deflate compression that's included with it. And so I think this is one of the last slides. This shows just there's multiple ways to get to do QAT offload. There's a direct API. You can go through zlib or OpenSSL through various patches, and there's a kernel interface. And that's it. Any questions?
Great, thank you. Questions for Greg? Go ahead. Yeah.
When you were speeding up the erasure coding computations, do you have any numbers on how does that improve IOPS? You quoted CPU utilization, but like how significant is the CPU part compared to the communications and all that other stuff?
Yeah, I wish Tushar was here for that. Well, yeah, I understand it's actually hard to stress the system enough to see under these circumstances. Maybe there's more extreme circumstances other people have done, especially when they've done huge number of parodies. But doing it in these circumstances, I understand it was fairly difficult, and so they had, especially using SSDs and NVMEs. It was just tough to keep up. So that's why he presented just the numbers. Mostly you can see sometimes with CPU utilization more than you can see the bandwidth differences.
Any other questions for Greg? Okay, let's thank Greg. Thank you.